Hello YouTube, this is going to be part 8 of how to build a Raytracer from scratch in C++, and this is probably going to be the last video. This is where we left off in our previous video with our first rendering from our Raytracer. I ended it because we had gone on for a really long time, so I'm going to start back up right here, right where we left off. We created this image by first looping through a nested for loop, and at each pixel we created a ray that started from our camera, and we sent that ray off into the scene. And then we checked through our objects in our scene to see if that ray intersected with anything, and then we went from that intersection to the light source. If we encountered any other surfaces between our intersection point and our light source, then we scaled the color of the object at that intersection based on the normal direction and other parameters such as ambient light, and from that we were able to create a rendering with shadow. So this tutorial I'm going to show you how to add a tile pattern to the floor, which is extremely simple. Then I'm going to show you how to add reflections, which is going to be a modification to our final color value. And then I'm going to show you the very simplest form of anti-aliasing. So anti-aliasing, if you'll notice along the edge of our sphere, you'll see it's pixelated. And the reason that it's pixelated is because we sent one ray through each pixel, and the color of that pixel became the color that we wanted it to be. So what we're seeing here is the color accuracy down to 1 pixel. If we want to smooth out this edge, around this edge here, that would be anti-aliasing. That would be, in terms of programming, it would be averaging the color over multiple pixels sent off within to another image plane behind our first image plane. So simply put, we're going to add another level to our for loop where we send multiple rays into each pixel, and then the color of that pixel is going to be the average of the colors returned from those rays. So it's resolving our accuracy of our color to a smaller scale than just 1 pixel, or it's the illusion of doing so. But first, let's add the checker pattern. So we have our color class, we have the special value, and we're going to let a special value of 2 correspond to our checkerboard. So instead of changing the color by modifying the final color value, we're actually going to change the color of the object based on an algorithm. So here we have the winning object color. We're going to change that color. So if the mod of 2 of the square variable is 0, it's going to be a black tile. So we're changing the color of the winning object to black at that pixel. Otherwise, white tile. So we've simply modified the winning object color at that pixel. Now we can change the special value of our plane to 2, and that changes our plane to a checkered tile. We change the special value of our color. Let's compile and see if we have a checkered floor. So we have this interesting tile floor effect now, and you see that it's a yellow tile floor. That's because of the color we have set our maroon to. So if we change the color of that to white, we should get a white checkered floor. We'll leave maroon the color that it is and create a new color. And change the color of our plane to tile floor. There we go. Now we have a checkered floor pattern. I'd also like to add the feature of being able to know how long it takes a rendering to be generated. So this is a very simple thing. We added a header in our file to include time. And that should return the amount of time that it takes the rendering to be produced. And you see it took our rendering 2.8 seconds. Now we're going to add reflections. And this is going to be actually modifying our final color value in a similar way to modify it to the way that shadows modified our final color value. So we go into our get color at function. Before our test for shadows for loop, we're going to add another for loop. Well, this is going to be how we see what our ray intersects with first in order to determine which direction the ray goes off in order to have a reflection. So the way reflection works is a ray comes out of our camera, it intersects with an object in our scene, it reflects off of that object, and then it intersects with another object in our scene. If it intersects with another object, we have a color of our secondary object, and then that's going to get added to the color of our first object. So it's going to be modifying the winning object color by adding the color of the object that reflected off of our secondary ray, and that is going to be what we return to our pixel. So if the ray intersects off of our sphere and it's reflective, and then it intersects with our plane, which is a white tile, then we're going to add the white tile color to the color of the sphere, and that's going to give the illusion of reflection. It works quite nicely. Oh, sorry. No, that was right. First we have to handle the reflection off of objects that have a spectral value. we have to find our reflection direction again. But instead of creating a shadow ray, we create a reflection ray. Determine what the ray intersects with first. Where we have to create a array of reflection intersections. We have to put the intersections with our ray into our reflection intersections array. Compile. We haven't modified our final color value yet. So, for each intersection, we have to go and see if it intersects with anything else along that path. And then we have an array of intersections, and we find the intersection with the winning object. We want to find the winning object in the array of reflection intersections. So if we get a -1, that means the ray missed the reflection ray didn't intersect with anything else. We don't want any intersections that have a value less than our accuracy value. Ray only affects the color if it reflects off something. So you'll notice that we are in our getColorAt function, and we're making another call to getColorAt. That's because reflections are an inherently recursive process. Within each reflection, you have to create a recursive getColorAt routine. So each reflection can go off into multiple directions, and then you could intersect with another object, and then the ray could bounce off of that object and go off into other directions. And each time you do this, you're creating a recursive call to the getColorAt function. So all of these processes of modifying values in order to create shadows and reflections happens at each reflection point. So we added our getTime feature to our command prompt so that we could see how long it takes for a rendering to take place. And you'll notice that after we add reflections, it takes considerably longer to render an image. And that's because of these recursive calls. Once we add anti-aliasing, it's going to take even longer because we're now creating multiple rays from each pixel. Now we modify the final color value. We've modified the final color to include the reflection color. Sorry, I don't know where I'm reading that from. That's right. So we're modifying the final color value based on the special value that we assign to our spectral intensity. Ray tracing is a complicated process, so don't be discouraged if you can't understand some of these linear algebra equations. Let's compile, see if we have any errors. And now we need to assign a color to one of our objects that has a special value corresponding to reflections. So, which we've already done that. So our special color is this pretty green color. So our pretty green color has red, green, blue value and a special value. if we had assigned maroon to the sphere, it would be neither shiny nor reflective. But in this case, we want it to be reflective. So let's render our image and see if we get reflection. Uh-oh, that's not good. So I had to pause the video for a minute in order to find a bug. Turned out it was a simple error in logic on my part. It's causing the program to fail. Here I had index of winning object reflection equals -1. I was supposed to have this to be not equals -1. That simple change in logic. We can re-render our image. And let's see if our reflections work. And our reflections work nicely. So at this point you could create multiple objects in your scene, multiple spheres, and the reflections would show the reflections of the other spheres. So let's create another sphere and see if we can see the second sphere in the reflection of the first sphere. Since we're no longer using this maroon value, we'll put that maroon value on a sphere. First will be the case where it's not reflected. Second sphere is not reflected. Now we have two spheres. We need to place this sphere at a different location. This new sphere location. Where instead of being the origin, we'll let that be slightly to the right of the first sphere. Which would be, we'll try 1 in the x direction, 0 in the y, and 0 in the z. In other words, the new sphere location might be the same as this x coordinate. You notice with two spheres it was, one sphere it was 2.8 seconds. With two spheres it was 3 seconds. And now you see our second sphere is on top of our first sphere, so I need to move it a little further over. I can make its radius smaller too if I wanted to. I'll give it half the radius. So you can now see the reflection of our second sphere on the first sphere, right here. So all it's doing is it's adding the color, this maroon color, it's adding that value to the value of the sphere color at this pixel, which is a very simple algorithm that creates a very realistic illusion. The only thing left that I can do now and show you is how to add anti-aliasing. You could of course add more objects into your scene. All you'd have to do to incorporate other objects is add classes for cones, add classes for cubes, add classes for cylinders, and then you could start to think of surfaces in terms of polygons. And then once you can think of polygons, you could have a scene file to where you'd have vertex positions of your polygons in a scene file, which would replace our calls for scene sphere and scene plane. You could replace those with a scene file, and the scene file would actually have your objects in it. So I'm just talking about ways you could extend this ray tracer that I can't show you how to do. But what I can show you is anti-aliasing, and that will clear up a lot of this stuff in the background. You see the way the black and white is becoming squiggly in the background. You can clean that up quite a bit simply by adding anti-aliasing. So we started our entire ray tracer by creating two for loops that loop through each pixel. We're going to add another two for loops to trace more pixels through each pixel. So you could have 4 or 9 or 16 pixels going off into slightly altered directions within each pixel. And these you can get an average color from, and those will be returned back to the color of the pixel as an average, and your final rendering will just be much smoother and cleaner because of this average. So an AA depth of 0 would correspond to what we have right now, and an AA depth of 1 is going to correspond to sending out 4 pixels, or 4 new rays at each pixel, and getting the color average of those 4 rays, and then the final color is going to be an average of those. You'll see whenever we have a rendering that's anti-aliased, and we'll compare it with a rendering that's not anti-aliased. Where the size of this array is AA depth squared. We'll start with a blank pixel. So what I'm doing is I'm taking everything that's highlighted and I'm wrapping it in another 2 for loops. AA index is similar to this one. But it's for this layer. So we had a routine here that we used to create perspective, and all that we did was we offset values from the direction that the camera was pointed based on the height and width of the image. We're going to put that inside of another if statement so that we can say if the AA depth is 1, then we have this simple case, and if the AA depth is greater than 1, we have anti-aliasing. So an AA depth of 1 corresponds to no anti-aliasing. Otherwise, anti-aliasing. It's going to be a very similar routine to our other perspective routine. Except we change this 0.5 value to a different value. All we do is we change this 0.5 to this double AX divided by double AA depth minus 1. Now all we have to do is average the pixel color. So we replace this pixels with temp red, temp green, temp blue. Replace this one with AA index. We do the same thing where we made our first call to get color at. Replace pixels, this one, with temp red, AA index, temp green, AA index, and temp blue, AA index. 3 short for loops. And then the variables index red, index green, and index blue. In each of these loops, we say so that the total red value becomes the red value from each ray, and then the total green value is the total green value from each ray. And total blue is total blue from the blue ray. Red equals total red divided by the number of pixels that we traced, which is the AA depth squared. So, if AA depth is 1, then total red is divided by 1. If AA depth is 2, total red is divided by 4, because that means we sent 4 rays out into that 1 pixel. If we changed AA depth to 3, then that means we're sending 9 rays out into each pixel. Average green, average blue. Finally, we return to our pixel and say this one dot red equals average red. This one dot green equals average green, and this one dot blue equals average blue. And if all goes well, you should be able to save an image. I'll call it scene Anti-Aliasing. See if we have any errors. Temp red is not a strut like our pixel value. It's just an array. Same thing down here. So we have two images here exactly alike. That's because in the first one we have AA depth of, we didn't have AA depth, and in the second one we have AA depth of 1. So if we increase our AA depth value, we should get a better looking image, but we'll see our render time skyrocket. AA depth 2. So you see, simply from going from an AA depth of 1 to an AA depth of 2, we made the render time go up by a factor of 4, from 3 seconds to 12 seconds. This is our original image. This is our anti-aliased image. It's not very good yet. We can make it a little bit better. It's going to go from 12 to probably 48 seconds. And remember, this is just an approximation of anti-aliasing. A full-blown Raytracer would take a lot of experience and knowledge about light and computer models in order to create a proper image. So that one took 27 seconds. Original image, anti-aliased image. Now we're starting to look quite a bit better. We'll do one more at an anti-alias depth of 4. So that means for each pixel, we're gathering 16 colors and averaging them. It's going to go from 27 seconds to probably a minute or more. So you can see how rendering times can start to build quadratically simply by having these nested for loops. For a real Pixar feature film, they have individual frames that can take hours to days to render. That one took 49 seconds. There's our original image. There's our rendered image with an AA depth of 4. There's the original. There's AA depth 4. So you can see we've cleared up quite a bit of the squiggly lines in our checkered pattern on our floor. There are other things we can do to clear this up as well. We could put another image plane at the back of the field of view that's not quite infinitely far away. We could put an image plane, say, 100 units or 200 units away that's black, and it would effectively cut off all those squiggly pixels because they wouldn't be something you could see. So computer graphics is about illusions of the eye altogether. And these illusions are created with linear algebra. So I hope you guys enjoyed my tutorial on ray tracing, and I hope you guys keep programming and keep learning. Thanks for watching. Bye.